Welcome to the deep dive. We sift through stacks of information, pull out the key insights, and basically give you a shortcut to really understanding complex topics. Today, our goal is to sort of demystify how something like a self-driving car or maybe a robotic surgeon actually, comes together, piece by incredible piece. We're going to plunge into this really fascinating interwoven world: STEM robotics, artificial intelligence, machine learning, and computer vision. Okay, let's unpack this. We should probably start right at the foundation, right? When we think robots, our minds often jump to sci-fi stuff maybe, but the actual journey from just raw materials to a machine that's genuinely autonomous, well, it starts with some fundamental physical ideas. At its core, robotics is the field focused on designing, building, operating, applying these programmable machines that can carry out complex actions, autonomously. But that autonomy, it isn't magic. It's built on some incredibly precise engineering. So what are the key physical bits, the control elements that actually give a robot its abilities?
Exactly. That's a great starting point.
Yeah.
Because before a robot can think, it needs a body, right?
Yeah.
And a way to control that body. So you have the mechanical systems. These are the physical parts, the limbs, joints, the actual structures. They give the robot its shape, its form, and let it interact with the world. Think of it like the skeleton, maybe the musculature. Then you've got actuators. These are the real movers. They convert energy, usually electrical, into physical motion. They're essentially the robot's muscles. And of course, for a robot to know anything about its surroundings, it needs sensors. These are its digital eyes, ears, maybe even touch. They let it perceive the environment around it.
Okay, so we've got the structure, the sort of muscles and bones, and then the eyes and ears with sensors. Got it. But what tells those muscles and bones what to do? Especially based on what the sensors are picking up. That must be where control systems fit in.
Precisely. Yeah. The control systems are the algorithms, the software. They act like the robot's nervous system, you could say. They dictate how all those actuators coordinate to get the movement and behavior you want. They translate these high-level goals, like pick up the cup, into very precise physical actions. And crucially, these systems almost always rely on feedback loops. It's like a continuous conversation. The robot does something, the sensors report back on how it went, and the control system adjusts. It refines its movements constantly on the fly.
Ah, okay.
That's how a robot keeps its balance, for instance, or tracks something that's moving.
That real-time adjustment, yeah, that sounds absolutely critical. And how does a robot figure out how to move in space? Like knowing where its arm is or where its hand is relative to its shoulder? I think that gets us into kinematics and dynamics.
Yes, exactly. Kinematics and dynamics. They're kind of the unsung heroes of robot movement. They are the mathematical tools, the frameworks that describe how a robot moves and the forces involved. So imagine a robot arm. Kinematics focuses just on the geometry, how the angles of its joints translate to where its hand ends up in space. We talk about forward kinematics. Joint angles, you calculate where the end effector, the gripper, say, will be. Simple enough. But then there's inverse kinematics. That's much harder, but it's essential for almost everything useful. It's the reverse problem. You know where you want the gripper to be, and you have to figure out the exact joint angles needed to get it there.
Okay, yeah, that sounds way more complicated.
It is, but it's why a robot can, smoothly pick up an object or perform delicate tasks. It translates these abstract goals into very specific physical motions.
Right, so the physical design, the mechanics, the control, that's all fundamental. But a robot needs more than just a, let's say, well-built body. It needs to think, to learn, make decisions. And this is where things get really interesting, I think. This is where artificial intelligence and machine learning start to transform these mechanical systems. AI itself, it's come a long way from, just basic rule-based systems. What's the big shift that lets modern AI actually learn and show what we call intelligent behavior?
Well, artificial intelligence, AI, is the really broad field, right? It's all about creating systems that can act intelligently, learn, solve problems, make decisions. The big shift you mentioned, that's largely down to machine learning ML. It's a subfield of AI. Instead of us humans trying to program every single rule for every possible situation, which is often impossible, ML lets computers learn and get better from experience. They build predictive models directly from data. It's more like teaching a computer by showing it examples rather than giving it this massive, rigid instruction book.
Okay, teaching by example. And within machine learning, I know there are different ways these systems learn. We hear about supervised and unsupervised learning a lot. Can you just quickly break down the main difference there?
Sure. Supervised learning is kind of like having a teacher. The algorithm gets trained on data that's already labeled, meaning the correct answers are included with the data. So the system learns the connection, the mapping between the inputs and the correct outputs. Then it can make predictions on new data it hasn't seen before.
Like showing it pictures labeled cat so it learns what a cat looks like?
Exactly like that. That's a classic example of classification, putting data into categories. Or it could be regression, like predicting a future value, maybe a house price based on features.
Okay, so if supervised learning needs labeled answers, unsupervised learning sounds, well, like it's figuring things out on its own, maybe finding patterns we didn't even know were there.
That's a great way to think about it, actually. Unsupervised learning algorithms work with data that isn't labeled. There are no right answers provided beforehand. It's like sending an explorer into unknown territory and asking them to just map out what they find. Its job is to find structure, patterns, features, all by itself. A common example is clustering. The algorithm groups similar data points together without being told what the groups should be.
Ah, like finding customer segments, maybe.
Precisely. Or finding unusual patterns in network traffic that might signal an attack. Another one is dimensionality reduction. This is like taking a huge, complicated data set and boiling it down to its essential features, making it easier to understand and work with without losing the critical information. It can definitely uncover things humans might miss.
And then there's deep learning. That seems to be everywhere now, powering so many AI breakthroughs. What gives it that extra power?
Yeah, deep learning has been a game changer. It's a specific type of machine learning that uses artificial neural networks with many layers, hence deep. What makes it so powerful is its ability to automatically learn really complex patterns and hierarchies directly from raw, unstructured data. Think images, audio, natural text, things that are hard to define with simple rules. It's a bit like how our brains learn building up understanding layer by layer. Instead of telling it, look for whiskers, pointy ears, tail for a cat, you just show it tons of cat pictures and it figures out the important features itself.
Okay.
Key examples are convolutional neural networks, CNNs. They're brilliant for images, kind of mimicking how our visual cortex works using filters to find patterns. And then you have recurrent neural networks, RNs. They have a kind of memory which makes them good for sequential data, like language, where context matters. The meaning of a word depends on the words around it.
Right. And speaking of language, that brings us to NLP, natural language processing, another huge piece. How does AI even begin to handle something as complex and nuanced as human language?
NLP is fascinating. It's the whole field focused on getting computers to understand, interpret, and even generate human language. It's all about bridging that gap between how we communicate and how machines process information. This is what's behind speech recognition on your phone, or sentiment analysis that figures out if online reviews are positive or negative, and of course the really sophisticated language generation you see in modern AI chatbots. And what's really fascinating here, connecting back to robotics, is the huge shift ML brings. It lets robots learn and adapt from their surroundings instead of just rigidly following pre-programmed steps. This is how a robot arm might learn to pick up some weirdly shaped object it's never seen before, just through trial and error. Or how a self-driving car learns to handle constantly changing traffic. It takes robots from simple automation towards, well, genuine adaptability.
Okay, so we've built our robot. It has a solid body, precise controls. We've given it a brain using AI and ML so it can make decisions and learn. But how does it actually see? How does it interpret the messy, dynamic world around it so it can navigate and interact safely? That must be computer vision.
Exactly. Computer vision, or CV, is the field that gives computers the ability to see, to pull meaningful information out of digital images and videos. It's really how robots get a sense of sight, allowing them to understand the visual world.
Now, people sometimes mix up computer vision and image processing. Is there a key difference? It sounds like they might be related, but not quite the same thing.
That's a really important distinction to make. Image processing is more about analyzing and manipulating the image at the pixel level. Enhancing contrast, removing noise, finding edges, maybe correcting defects. It's about transforming the raw image data itself.
Okay, making the picture better or clearer.
Right. But computer vision aims higher. It takes that processed image, often, and tries to understand the semantic content. It's not just about the pixels. It's about figuring out what is in the image, what objects are there, where are they, how do they relate. It's about extracting meaning.
Got it. So CV is about understanding what the pixels represent. What are some core tasks CV performs, especially for autonomous systems?
Well, a huge one is object detection. This means identifying specific objects, people, cars, dogs, whatever, within an image or video, and usually drawing a bounding box around them to show their location.
Like a security camera that flags person detected?
Exactly that. Common ways to do this include region-based methods. These first propose likely areas where objects might be, and then they analyze those areas more closely. Or there are sliding window approaches, which are a bit more brute force, just scanning across the image, checking small patches.
Okay. And I've also heard of semantic segmentation. That sounds even more detailed.
It is, yeah. Semantic segmentation goes further than just drawing a box. It tries to classify every single pixel in the image into a specific category. So it doesn't just say there's a car here. It outlines the exact pixels that belong to the car, the pixels that are road, the pixels that are sky, the pixels that are a person.
Wow, okay.
This gives a much richer understanding of the scene, which is vital for things like self-driving cars that need to know precisely where the road is, where the sidewalk starts, where pedestrians are. Pixel-wise, classification is key. And then you could even have instant segmentation, which not only identifies all the car pixels, but also distinguishes between different cars. So car number 1, car number 2, not just a big blob labeled car.
Right, that makes sense.
So if you connect this back to the bigger picture, computer vision is absolutely fundamental for robots to interact intelligently and safely with the world. Without it, autonomous systems would essentially be flying blind. They couldn't navigate, avoid obstacles, manipulate objects, or even tell a person apart from a tree. Visual understanding is key.
Okay, so we've looked at the robot's physical body, its AI brain, its computer vision eyes. Now, let's try to bring all these threads together. How do these pieces combine to create this powerful symphony, this STEM integration and AI-powered autonomy?
Well, STEM integration itself is really about that holistic approach, right? Combining science, technology, engineering, and math together, not treating them as separate silos. And that integrated way of thinking is exactly what you see in advanced robotics. It's not just an engineering challenge or just a software challenge. It requires expertise across all those STEM fields working in concert.
And that synergy, that working together, it really comes to life when we talk specifically about robotics and AI, doesn't it?
Absolutely. Robotics and AI signifies that deep integration of artificial intelligence techniques, especially machine learning, right into the design and control of the robots themselves.
Yeah.
This is what allows the leap from robots that just follow pre-programmed paths to robots that can actually perceive their environment, learn from it, adapt to changes, and interact intelligently.
Wow.
It's moving beyond just repeating tasks to, well, figuring things out.
And that capability, that figuring things out, that leads directly to the ultimate goal, right? AI-powered autonomy.
Exactly. AI-powered autonomy is the endpoint, you could say. It's the ability of these robotic systems to operate independently, to make complex decisions, navigate complex environments, all without direct human control. And it's those advanced AI algorithms that make it possible. Think of fully self-driving cars making real-time choices in traffic, or autonomous drones mapping hazardous areas without a human pilot anywhere nearby. It's about genuine operational independence.
And computer vision specifically, while crucial for robotics, also has this broader role within STEM generally, separate from robots sometimes.
Oh, definitely. Computer vision in STEM is huge. It refers to using image and video analysis across all sorts of scientific and engineering problems. It's critical in scientific imaging, analyzing microscope slides in biology, or telescope data in astronomy. In engineering, think about industrial inspection, automatically spotting tiny flaws on a production line that a human might miss.
Right.
It's used in environmental science for remote sensing, analyzing satellite images, even in fluid dynamics modeling. So while it's totally integral to making robots see, its applications stretch way beyond that into nearly any field where you need to understand visual data. And we're seeing even deeper integration now in areas like robot learning, where robots get better at skills through practice, essentially. And cognitive robotics, which is really ambitious, trying to give robots more human-like reasoning and understanding. But the real magic, the truly transformative power, it really lies in that deep, synergistic integration of all these fields, the mechanics, the control, the AI, the vision. That synergy allows robots to go way beyond simple automation. They become intelligent, adaptive, autonomous systems. And this isn't just about building cooler gadgets. It's fundamentally changing what machines can do, which has massive implications for, well, almost everything: healthcare, manufacturing, exploration, daily life.
Wow. What an incredible journey we've taken today. Seriously. From the, the nuts and bolts of a robot's body through the complex AI giving it intelligence to the vision systems letting it perceive the world. We've really unpacked those intricate connections between STEM robotics, AI, machine learning, and computer vision. Hopefully you listening now have a much clearer picture of how these fields weave together to create these amazing autonomous machines that don't just follow commands but can actually learn, adapt, and make their own decisions.
Absolutely. And maybe a final thought to leave you with: as these incredibly capable AI-powered autonomous systems become more and more a part of our world, Just consider the sheer number of ways this synergy might redefine things, not just industries, but maybe even our day-to-day interactions with technology itself. As machines get better at truly understanding and engaging with our complex world, what kinds of new human-robot collaborations might actually become possible? We're really just scratching the surface. The possibilities are just starting to unfold.